and thanks for the invitation. It's my great honor and so exciting to talk at ML conference because this is really the experts are here that daily thinking about how to apply ML in the EDA or the design applications. So maybe you don't, for the previous couple of years at ML conference, you don't see too many papers on how to apply machine learning on multi-physics domain. And so today, I will talk about what's the needs coming from customers and what we can do possibly to apply machine learning in the multi-physics domain. And first, let me introduce ANSYS. ANSYS is a more than 50 years old company. Started with ANSYS Mechanical. And ANSYS Mechanical started at Pittsburgh. And along the way, ANSYS acquired computational fluid companies such as Fluent, Ansoft, and then acquired our company, Apache Design Solutions, in 2011. So we are on a pace of acquiring pretty much about 3 to 5 companies every year. And so now it's more than about 6,000 employees, and we cover pretty much all the areas. And we have more than 4,000 customers. And the revenue is about $2.2 billion yearly. And the market cap is about $28 billion. So per se, it's not a very small company. So we cover a lot of areas, starting with in the industry coverage, in the aerospace, automotive, healthcare, energy areas, and also the high-tech, the areas that we are in, including the electronics and the semiconductor areas. And we have a lot of tools covering different areas. But the basic convergence of the tools that we share with all the areas, including the computational fluid dynamics, mechanical for the construction, and a lot of physics, and also the semiconductor and electronics, silicon photonics, optical area. So a lot of multi-physics in our tool set, and we provide the processing and the data management as well. And that's why we acquired the Granta for material foundation to provide the material intelligence, including the machine learning applications. And in my BU, that we belong to electronic semiconductor and the optics BU, that also including the silicon photonics, which we will focus on today. So we'll cover several areas today. These are the 4 areas of the machine learning that we are working on. That started from the organic development of the machine learning algorithms to speed it up our solvers, and also for the co-optimization. And so I will talk more details about that, give you some examples. And the top-down methods means that we can apply a black box co-optimization algorithm, such as from the company called OptiSLAM that we acquired 5 years ago. And we also have a hybrid digital twins and reduced order modeling, which is a very strong suite for the ANSYS technologies that looking at linear time invariant, linear parametric variation modeling, and we provide a digital twin. So I'm not going to talk too much about reduced order modeling today. And the other area that I will touch a little bit is ChatGPT LLM. Last night we have a lot of great discussions. We talk about a lot of quite a few applications. So I will talk about what's the effort that we are going on for the application of the LLM in this area. So there are a lot of LLM models that develop every day. Mark told me that NVIDIA is coming out Nimble next week. And so that we can see that continuously from Meta, from Google, from NVIDIA, from IBM, even from IBM this morning, there's a LLM model coming up. It's all based on the transformer architectures. And if we look at the Silicon Valley startup, there are a lot of startups that are focusing on LLM. I talked to a few startups. Last week, talked to LLM for cyber security application areas. And last night, I think we catch a very important point that if we use a foundational model as a generic LLM, it will not go too far, too well for a domain-specific LLM. So people are looking at developing the domain-specific LLM, especially in Silicon Valley. So there are quite a few startups focusing on the persona, different persona for the LLM applications, for LLM for doctor, LLM for lawyer, LLM for cybersecurity, as I mentioned. And they all get a lot of funding, like $81 million for that company. And LLM for, why not LLM for VLSI? We haven't seen that. And so that could be a possible idea. Or maybe they are start working on it already. So I mentioned a couple start last night. And so the domain-specific LLM, I think, is the way to go. And the other idea is that the Copilot for all the persona in terms of the VLSI or the EDA developers, the Copilot for simulation, that can help customers to look at the log files, and if there's an error or the warning, and can tell customers what to do next, and can perform the diagnosis as a simulation Copilot, and can guide customers through the whole flow, as demonstrated by Professor Bayu. And interactive Q&A is a part of it, right? That if customers are asking different kind of questions, and you can do an interactive Q&A to guide the users how to use the tool, generating the specific command sequence, or even writing the code for customers, writing Python code or the Tcl code to execute the EDA workflow. And I talked about a couple of applications also last night. I think it's a great applications, the RTL synthesizer, and they are like a Flux Copilot and also Rapid Silicon are the two representative companies in startup working on RTL synthesizer. And the Spice Stack test circuit to detecting the floating node or the short or the leakage power for specifically for analog and mixing or design is a great application as well. The architectural domain-specific synthesizer, that's another great application. And you can look at that there are so many architectures already available. If you put in all the knowledge there and let the LLM, domain-specific accelerator to learn all this knowledge, it can be a great trade-off and a great paper as well. And depending on the customer's demand, by looking at the benefit, the performance, and also how much money are you willing to spend, then you can come out some of the optimized architecture. That could be a great application. So I'm going to talk about some specific applications that ANSYS are working on. Like 2 months ago, that we have a press release that we are coming out ANSYS GPT 2024. And this is very exciting. The ANSYS GPT will have the following goals. First, we will provide an interactive Q&A for customers. We saw thousands of questions coming in every day to our corporate support center. And we need to have AEs to answer those questions. And why not have an ANSYS GPT to answer those questions? And so there are a couple levels of ANSYS GPT that we are developing. The first level is based on the public data, the ANSYS public data, to develop the interactive Q&A for customers who are not yet customers or who are not yet customers for a specific tool. So they can ask a lot of questions about information about that tool, and they don't have a hands-on experience about that tool yet. And the second level is the ANSYS GPT will provide support for customers who are already users of the tool. Then you will go into a more detailed interaction to answer customers' questions. And that means that customers already have the tool. And the other application that we want to serve is that we also build an internal ANSYS GPT that will serve the purpose, helping the sales to understand the market and also to investigate that specific customer, what do they need, and what's their roadmap for the next 3 years. We can also generate the content for the marketing, for content creation, and also helping the ACE for our application engineer to have a more detailed interaction about the tool. And so there are several challenges about this ANSYS GPT. This is based on the data. For example, here is a public application, the public version, that we look at the more than 300 plus YouTube videos, and also 300 plus courses, and more than 10,000 knowledge articles that we can get, which is already public in the internet. And we train based on this model for the general interactive Q&A about the ANSYS tools. There are several technology barriers that we need to overcome. First is that the sources of data are diverse. So we need to use AI enhanced to filter the raw data, to remove the duplication of the data, and also have a specific, version specific, that if you ask 2023 R1 versus 2022 R2, the question will get a different answer, even if it's the same question. And we use a retrieval augmented generative architecture and to put in our in-context knowledge to help generating a much better answer. And the other question I mentioned last night is that we need to reduce hallucination coming from our ANSYS GPT by using a different kind of techniques, and also we need to handle the complicated question as well. So I have a couple more slides in detail. And our system is running on Azure Sandbox, and we also need to make sure that it has InfoSec approval, and also we can handle the ITAR information well. So that's probably everyone understands this architecture. This is a very common architecture that if you don't want to fine-tune the foundational model and you want to add additional knowledge to help train the system, that there are queries coming in from the customers, and also the knowledge that we provided based on those knowledge sources. That both sources of the knowledge will be going through a numerical vector embedding, and we will generate a vector store. And then we will try to find the most relevant information, maybe going through the LangChain or the Llama index. Then we will send the question, including the relevant knowledge, to the LLM. Doesn't matter if it's a Llama 2 or it's a GPT 3.5 or GPT 4.0. And then we will create the answer. And we also generate a voice interface. So this will be very exciting. Because some customers, they are speaking in Chinese or speaking in Italian, and not all our AE understand those languages. Yeah, so what causes a high IR draw in my design? So you can ask in Chinese or in any languages. The Whisper API is very powerful. It can understand all the language. It can translate into English and then ask the LLM in the English in the context, and we'll get an answer back. And there's a trade-off that we need to design, is that the Whisper API come with the small English version, medium English version, and also the large English version. Large English version running on the CPU will take 26 seconds, and running on GPU, of course, that takes 0.3 seconds. But the medium size of the English, it's a compromised best performance version. Running on CPU takes about 0.25 seconds. Running on GPU takes about 0.1 second. So we choose the medium.en. The compromise is that sometimes the certain accent that the system cannot understand by choosing the medium.en version. But it's very good. Whisper.api is very powerful in terms of the STT and the ASR technologies, so we are very happy about that. There are a couple of questions that we need to overcome. How do we guarantee the accuracy of the result coming from the ANSYS GPT? Or this is a system we are building for the semiconductor BU. So we use a solution that if you look at the prompt, I'm not going to read through. So we ask GPT 4.0 as a judge and as an unbiased judge. And you need to look at answer A and answer B, and give the answer A and answer B a score, and then to do a comparison. Which one provides a better answer compared to a reference answer? So we choose 20 questions, 30 questions, And then we talk to the application engineer to provide a golden answer. So as a reference cases, then we can compare GPT 4.0 generative answer. We can compare Llama 2 generative answer and 3.5 generative answer. So we will see clearly like which system performs better. And the answer is that GPT 4.0 still performs the best compared to all the LLM models. But this is a very good way for internal QA for your interactive Q&A system. So there are other couple challenges that we need to overcome. One is that how do we handle complicated questions? For example, this is one of the questions. How do we get the shortest path report from the system? So if you want to get the shortest path report in terms of the resistance calculation from a node to another node, and first you need to set up the command to execute the command to get the shortest path execution. Then you need to issue a command to view the shortest path in the GUI and also generating a detailed pin-to-pin report. So you put together for the decomposition of the complicated question, then you can, at the end, that you can put together all the individual answers into the final answers. So if you try the GPT 4.0, please decompose this complicated question into easier questions. It will do that automatically for you and happily. And so that can be one of the methods. So there are a lot of benefits that once you decompose into several questions, that for some questions that because of the saving the cost, you can use the 3.5, which is 10x less expensive by issuing a command to 3.5 compared to issuing a command to 4.0. 4.0 is 0.2 cents per click, and 3.5 is 0.02 cents per click. And you can also use some of the question, you can use a Llama 2 to answer the question. So you have a lot of flexibility. And the second question is that how do we reduce the hallucination? Now we can set a temperature equal to 0 by using the GPT 4.0. And we also use a trick, Answers GPT. We ask Answers GPT always come with the references that are combined together with the answer. So customers can double check where the answer coming from. Is it coming from a specific YouTube video or coming from a certain knowledge article? So now they will feel more confident. And the specific feel from our experience that if you have a specific collection of the Q&A, we have a lot of Q&A with the different customers because we have so many customers. And some questions coming from, for example, from Intel, it has some confidential information about the Intel's design methodology. So by looking at thousands of the Q&A pairs, we need to desensitize the customer sensitive information. And then we can filter through the sensitive information. By the end, we have a specific Q&A pairs, and that will be very valuable for training, and that will provide a very good answer, provided specific questions coming from customer. The other method that we can use is that Llama index that it has the default top k equal to 2 return, and we can tune the different parameters. Let's say top k equal to 4. So we will get to see more relevant documents coming in before we can ask the LLM model. So that's a snapshot of the effort that ANSYS and also our semiconductor BU are overtaking using the LLM model. We are also working on the MapReduce code generation. MapReduce is a distributed computational platform for the C-scale. And then users have to write the MapReduce Python code painfully. And so we are thinking that if we can automate that process by generating the MapReduce code automatically, provided the natural language question from customers. So the following slide, let me talk about the machine learning efforts. We started this effort about 2017. I remember that I initiated the first workshop, and Andrew is one of the speakers at that time, 2017. Yeah, thanks. And so at that time, we got together different people from different BU. We don't have any machine learning effort in 2017. And so that's the first 2 days workshop at ANSYS that we invited the academic speakers and as well as industry speakers. And we'll try to see that if we can start it, the machine learning effort. So very happy to say that right now we have a lot of machine learning in our products, such as Quanta MI for root cause analysis in the material, diagnosis, discovery line, very fast running on GPU, and also the LS Dyna for automatic crash simulation and composite fiber simulation, and the mechanical for resource estimation. And so I'm not going to talk about the other applications. There are quite a few papers there. I will be focusing on the electronics and also the semiconductor applications in terms of the machine learning and what kind of effort we are putting in. So we have a concept of the open and extensible interface with all our multi-physics solvers. If you look at our ecosystem, we are working closely with Synopsys for the Fusion compiler, 3D-IC compiler with the 3D-IC system. We are also working with the Cadence in terms of the silicon photonics for the virtuoso platform, and as well as working with the Keysight for the ADS system in terms of high-frequency simulation. So we have an open source tool called the PyAnsys. PyAnsys has a certain specific API that you can download today, and you can look at the PyAnsys. And PyAnsys, when it is realized in different tools, it becomes a PySyscape, which is the dynamic IR drop is running on for the very hard SC platform. And if PyAnsys is running on AEDT, by combining specific APIs coming from the AEDT, it becomes a PyAEDT. So there is a PyFluent and PyAPDL and Py different tools. So we have a customization of a PyAnsys on all the tools. And on top of that, we also acquired companies 5-6 years ago, and it's called OptiSLAM. Very powerful, and they have more than 100 customers, so I'll talk a little bit about that. And I can serve the code optimization, very powerful and very useful. So this is a new box that we are putting in that by utilizing and exploiting the benefit coming from the LLM for the interactive Q&A, the code generation, and maybe some other applications that we are thinking about or coming from the request of the customers. That can be one way as well. So let me talk a little bit about the OptiSLAM and what's the underlying theory for this powerful code optimization auto ML platform. That OptiSLAM is an optimization tool that started with a design experiment, for example, using the Latin hypercube. And it can interface not only with the ANSYS multi-physics simulation tools, it can also interface with all the other tools from other companies. So first of all, you define the input, how many input parameters that you want to do the study of the sensitivity and the optimization correlated with a specific set of the output. And the number of inputs can be up to less than 200, and the number of output may be less than 50. That would be an optimal execution space for using the OptiSLAM. So internally, that based on the design experiment, and we look at the generation of the sample. For example, 1,000 samples. We take the first 200 samples to build a meta model, so-called adaptive meta model of prognosis. And by looking at the result coming from the coefficient of prognosis, which is the evaluation matrix to see how effective or how accurate the model generated is. And if you look at, say, certain areas, the red area and is not good. Red means not good, and then or the blue area means not good. And then we can generate more data through the design experiment, and that's why we will build a new adaptive meta model by automatically filling the missing data in that certain space, so we can build a much better model. It has a great capability to do the correlation between the input and output as well. So it will give you a sensitivity ranking that which inputs are most correlated with the output. and what's the explainability of the input versus output. So we'll give you a very good diagram here. And let's see what kind of algorithms are included. Itself has more than 30 algorithms in the toolbox. So it pretty much has all the statistical algorithms, also including the deep learning algorithms, and also the infinite mixture of a Gaussian process, the signal meta model prognosis to handle the S parameter. So by using this tool, you can select all the algorithms given input and output, and the system will automatically select a specific algorithm which is the best suitable for your application. And so this is a black box usage, you don't need to worry about which algorithm you are going to use, just choosing all the algorithms. Yeah. And you can also put in your own algorithm. So if you have a customized algorithm, you think it's better than all the algorithms here, including the evolution algorithm, you can have a plugin your customized machine learning algorithm, and you can enjoy the coefficient of prognosis, also enjoy all the reporting coming from the automatic design experiment execution of the co-optimization process. And you can also choose a specific algorithm for the application. So the grand scheme that we are thinking about is that, let's say, this is an example of the 3D IC. And there are many input parameters, including the heatsink design, where you want to put the TSV area, and also how many layers in the interposer that you want to design, and where you want to put a C4 bump, and how many metal layers that you want to use for power ground grid construction, and where do you want to put the block power and the placement, and also the relationship between among the chiplets in the 3D IC. So there are many, many input parameters that you can play with, and the output parameters, you can say dynamic voltage drop is one of my objectives, or you can put in the peak temperature is another objective, and also maybe stress, or the thermal aware timing is another parameter. Like if you can define the output objective, then you set up the OptiSand, everything will be automatic. You don't need to worry about, and you don't need to guess what's the next step, what's your heuristic to design a co-optimization of the 3D IC system. You just let the system running through. You will take the initial samples, build a meta model, and then for the rest of the input combination, we will be using the meta model to quickly run through the rest of the input combination space. And then you can transfer this meta model for other applications as well. So once the meta model is constructed, you own the meta model, and you can transferable model that you can use for other applications. So it's very powerful. So this is a way that you can do a co-optimization combined with a customized machine learning model. And that will be interesting, let's say, for some professors with a PhD student to try out the customized machine learning algorithm, plug in and see how it works. It may save you 1 year of the coding and working on more important stuff in terms of algorithm. So let's look at some of the applications by using the OptiSand. The first application with Samsung, this is a mobile application processor with a package in a PC board, and there are multiple layers of the substrate. And the key parameters that we are looking at in terms of the input is the heat transfer coefficient, thermal conductivity, the chip heat package capacity, and also the density of the material for the different layers. So previously, the Samsung engineers will take them 2 to 4 weeks to come out the different design of the density of the material choices to come out the best design for the mobile AP under the constraint of heat change and temperature. But now it only takes 4 to 5 days to go through this co-optimization automatically, and then we can always find an optimal solution compared to the heuristics that you need to guess what's the best combination similar to DSO.io that can achieve. And the next application that with the Intel that is already published is that they are using the OptiSand and to help them to build optimal power ground grid construction. So in the early stage of the chip design that they need to design, say by using the metal 6, metal 9, what's the width and the pitches, where to put the power switches in terms of the placement. And then they have a certain goal, say maybe 2% or 3% for the static IR drop, or you can also apply to the dynamic IR drop. And let the system to run through to find the optimal solution for you. And say, so you can find what's the best solution, and it will give you the sensitivity. What's the sensitivity of these input parameters? Another application, it's a very common application, is the optimization of the eye diagram. Given 3D IC system, you always achieve that what's the eye diagram using your latest and the best I/O signal technologies. So first we can use HFS 3D IC. Now we can do the co-optimization based on the geometry sensitivity of the parameters. And by looking at the different parameters, then we can try to find the optimal solution. Once we have the optimal geometry design, then we can send it to the circuit simulation combined with the IBIS model and several other sensitive input parameters. Now we can come out the optimal circuit simulation as well. So this is a great application. Another very interesting application is the virtual digital twin. And this is just 2 months ago at the OptiScene conference. That Continental, they built many test boards, and they need to change the placement of the test board and also the different test chip. So they want to see what's the temperature distribution. And this is a very cumbersome because once they change it, they need to go to the lab to do the measurement. So if they can build a digital virtual digital twin using the reduced order modeling combined with the OptiScan, everything will be automatic. So they don't need to do all the measurement. They can do the virtual digital twin in terms of simulation first, and don't need to do the laborious and the tedious lab measurement. So this is a very good application. So the next, I will talk about some of our customized machine learning algorithm. Not all the problems can be solved by applying the OptiScan. For example, say for the large-scale thermal simulation for 3D IC, the input parameters is just too many. So I will focus on some of the applications that we are building. So here are a couple challenges for 5G, 6G combined with the gallium nitride or the digital domain. So to how to handle analog mixed signal design combined with the digital design in high power. That's one challenge coming from 5G, 6G industry. And the other challenge coming from HPC and cloud is that the power continue to rise above 300 watts, 400 watts, or more than 10,000 watts for a cerebral system. And also for the automotive, the focus is on the aging and reliability that need to survive at least 15 years. And so we can see the power continue to increase. And that's why there are several challenges that, as I mentioned. One of the most important challenges for 3D IC, the upcoming challenge is the temperature. And if you look at the SOIC on top of the CoWAS design, the SOIC can easily have more than 20 chips, 30 chips in the design. And this is an AMD design with a V memory on top of the GPU using the SOIC design. So temperature, according to a lot of customers, is a major concern that we need to consider. And so that's one of the challenges. Let me illustrate what is a thermal challenge in 3D IC. If you have a local hotspot from the top die and a local hotspot from the bottom die, if these two hotspots line up, you will suddenly becomes a global thermal hotspot. That means that the vertical thermal coupling will be coupled among each other, among the chiplet in the 3D IC. So from the experiment, we see that there will be an increase of 20 degrees to 30 degrees if you have a vertical thermal coupling and a thermal hotspot line up from the vertically stacked dies. And power is the source for the temperature, but when the temperature increases, the leakage power will increase because leakage power is an exponential function of the temperature. And when temperature increases, it will affect a lot of things in the 3D IC. Thermal-induced stress, thermal-aware timing becomes very important because the temperature gradient across the chiplet will be more than 25 degrees suddenly. on the same SoC, we only see the thermal gradient maybe 10 degrees, and so it's not very severe for thermal wear timing. So suddenly it becomes a serious problem. And when temperature increase, the EM, electron migration, will be impacted, dynamic voltage drop, SI, PI, eye diagram optimization, silicon photonics reliability agent. So here is the need from one of the needs coming from customer is that for the large 3D IC system design, for example, for the using the SOIC on top of the CoWAS design, that there are more than 20 chips, 30 chips in the 3D IC. How did you solve this? That if you use a dense mesh grid, say even using a 50 micron mesh resolution to solve the whole thing uniformly, you will take more than a day or two or more than that. So there's a need to do intelligent adaptive meshing, and that's what we are working on. That given the power distribution for the 3D IC, that we can do a transformation from the power to temperature to predict where is the thermal hotspot. Then we can put more dense adaptive meshing in the thermal hotspot area, and then the coarser meshing in the non-thermal hotspot areas. Then we can run through the whole system within 12 hours. And this is very powerful. So intelligent adaptive meshing is one of the strong needs for finite element method, that if you want to run through a very large system. Another need is dynamic thermal management, that particularly very important for Qualcomm, for example, that for the dynamic voltage frequency scaling. And the trend is that there are more and more thermal sensors on chip. For example, AMD is putting on 64 thermal sensors. But you don't know where to put these thermal sensors if you don't know where is the thermal hotspot. And if you put in the wrong thermal hotspot, you may have a thermal runaway. That means that the most severe location will have a temperature increase, and inversely, the leakage power will increase, and then you will run into the thermal runaway issue. So that this is the traditional solution by building the reduced order modeling, working with the Qualcomm and the Samsung, and by applying this ice pack combination with a very coarse grid on chip, that we can build a dynamic thermal management system. But the need is that for the fine-grained thermal simulation on chip. So this is the request from customers that given the power, transient power vectors on chip with block placement, how did you provide very fast dynamic thermal simulation on all the locations in terms of the 10 micron mesh grid resolution? So this entirely is a machine learning problem, because by using the finite element method, you will take more than 3 days for running the simulation. And this is the HIR roadmap I participate. There are some the future goal for the next 3 to 5 years. But there are two applications. One is silicon photonics right now. For example, from the press release that NVIDIA are working with the TSMC on COUPE, C-O-U-P-E, and they have more than 10, 20 thermal sensors for the silicon photonics system. So it's, the sensitivity is plus minus 1 degree. So it's very important to get the thermal simulation as the boundary condition for the PIC, and then you can run a very detailed numerical simulation for the waveguide and the photonics component. The other application with the Teledyne Advanced Test is that for testing the large scale 3D IC system, that's a new challenge, is that the thermal hotspot during the speed testing will move from one location to the other location within 5 milliseconds. So you have to predict where is the transient temperature hotspot. Otherwise, your control of the chuck temperature will not be imbalanced. And so this is a, and then you will have a yield loss. So this is a big question, a big problem, big challenges for the 3D IC testing. So in summary, there are several challenges after talking to all the customers, is that they need the architectural level, very fast thermal stress simulation, given the architectural design with different block placement and maybe the global routing, and what's the thermal perspective, where they need to trade off between design A and design B. Secondly, that when you have a detailed placement and routing, that they also want a very fast simulations in terms of the thermal and transient thermal simulation, and also, of course, dynamic voltage drop simulation. And then the reliability will come into picture as well, because it's all thermal related. Just a quick comment for PIN. We tried the PIN, and for large scale of the physics-informed neural network, it doesn't work too well because there are too many tiles for the large chip. And if we partition the tiles in terms of the 50 micron by 50 micron, not even going down to 10 micron by 10 micron, it has a difficulty to do the nice modeling. And that's why last year we presented a paper here is using subdomain partition, and then we have a trick that to conserve the flux conservation between the subdomains, so we can generate pretty good result. And this is based on the, it can be generating a very good result on a 200 micron mesh grid. Now, if you go down to 10 micron mesh grid, you will have too many input patterns variation, very difficult to generate. So for dynamic thermal simulation, we come out a method last year as well, that we can use a decay service by taking advantage of the linear time invariant theory. So we can take the partition of the tile, say 10 micron by 10 micron, by looking at the victim tile from the neighboring tiles. We can see what's the dynamic response from the neighboring tiles. And then we can collect this response, accumulate together to get a final response. A theory holds, so this works, and then you can decompose the solution into hierarchical simulation. And then you can decompose in the local level and the intermediate level by using the multiple algorithm and the global decay service model. And this way that you can solve a very fast dynamic thermal simulation, including the application on the 3D IC. So the other two applications I want to talk about is very happy to say that this is a very successful application of the group neural network application, and mainly to solve the multi-conformal dielectrics problem in the random walk for capacitance expression. So this is a very difficult for random walk to do the random walk involving the multiple conformal dielectrics. So by building a deep neural network that we can go through the random walk very quickly, and this has been certified by TSMC and is already in the product and also in the paper. So very good work here. The other work we had last year is that we applied to the security. So for the EM side channel simulation, by looking at the thousand of the point of interest, that we can use a neural network to identify what's the most important point of interest. And then we build a model applied to all the other point of interest locations to speed up the simulation speed. And we have a very good correlation, and also won the best paper at Host last year. So this is the framework we are using, that based on the CSCAP, which is a distributed computational platform, that we put in the XGBoost and also the scikit-learn and the TensorFlow in the system. So we enable R&D to machine learning engineers to build different kinds of applications for CSCAP, for semiconductor applications. We also published quite a few papers, and also upcoming ICCAP paper to solve the problem that when we apply the ML solver, how do we go down to 10 micron by 10 micron? Because ML solver is comfortable with the 200 micron mesh grid, but cannot solve the 10 micron by 10 micron. And how do we extend that application to handle the 3D IC in terms of the vertical thermal coupling? And that's another question that we need to solve. So in summary, there are three major applications of machine learning at ANSYS. First is the latest and newest LLM applications, and we are looking for different kind of applications using the large language model. And the first one is interactive Q&A that will be coming up next year. And secondary, that we are using the OptiSense and also integrating OptiSense into different tools to provide a co-optimization framework. So that will enable customers and also maybe enable PhD students that you can plug in your customized machine learning algorithm and do different kind of co-optimization experiments to speed up your graduation date. And the third application is that there are certain applications that we cannot use the OptiSend or the LLM. So we need to develop customized machine learning algorithm for certain problems that are requested from the roadmap or from the customers. So we continue to work on the customized machine learning algorithms for these special applications. So thanks a lot.
Thank you for a great talk. Are there questions from the audience? George.
I have two questions actually. For the first conclusion, you said that you compared your interface based on your internal language model with ChatGPT, and you said that ChatGPT is still more accurate or more powerful.
We don't have money to develop our internal LLM. So compare 3.5, Llama 2, the other models, and with GPT 4.0. So our conclusion is that GPT 4.0 still have the best answer if you don't go through fine tuning. So such as Professor Bayu, they go through a fine tuning using Llama 2, they can have a much better performance compared to the GPT 4.0. But you have to go through the fine tuning.
Okay. And then for the last bullet, you're using this machine learning based modeling techniques to make the simulations, replace simulations, make it faster. What kind of accuracy levels do you target with that?
Accuracy?
Yeah.
Yeah, that's a great question. That's the number one question we need to struggle with, right? And how did you apply the machine learning model for different stages? In the architectural level stage, accuracy can be maybe they are, what you will tell us, maybe plus minus 50% is okay in the architectural level. So we have a 15% to play with if we are using the machine learning model. During the sign-off stage, right? It cannot be more than 5%. 0%, yeah. Yeah. So maybe 2%, yeah. We beg our customers, say 2%. Then that's the level that we need to strive to achieve. So that's the number one question that we struggle with. Yeah. How do we provide accuracy under different inputs? Yeah. And so we need to look at a given input, and we have a new technique to look at a new input. We can determine how it correlates with our training examples. If the correlation is not super strong, we know that the result will not be very good, then we'll give a warning. And if it has a strong correlation, that we know the result, the predicted result will be pretty good, and then we can come out with the result. So we need to have a self-awareness of the accuracy coming out from the machine learning model.
Okay.
Any other questions?
A technical question. So I saw there was some kind of alignment. Did you try the vector database to align the original pre-trained GPT to the particular application in Ansys? I mean, or let me make my question
easier.
So, how do you align if you don't fine-tune the GPT, how you align the original pre-trained GPT to customize the Ansys custom?
Oh, just using the IAG technique. So we provide the in-context knowledge.
Okay.
Yeah, through the Llama index.
And maybe last question.
So you mentioned somewhere that maybe you bring in some textbooks, technical textbooks. Right? Have you worked out some model with Springer or whomever, what it means to use that?
The textbook is our Ansys public information, the knowledge articles. So we have more than 10,000 knowledge articles on the YouTube. So the YouTube, you get it in, Llama index can handle the YouTube videos by separating into the text and the images, and then we can get it in.
I have one tiny question. Are there any limits, like 2% or 10 micron grid, that in your heart you know will still have as challenges that are open, let's say 5 years from today?
Yeah, I think it will continue to be
what are those?
I think it will continue to be a great challenge for the next 3 to 5 years. We haven't found a great machine learning algorithm. Theoretically, it can comprehend all the possible patterns. So that's one of the major challenges. During the training, how did you comprehend all the possible patterns? How did you guarantee the accuracy of your machine learning model? How did you let customers feel confident that this machine learning model is as good as a finite element method? That's a huge challenge. I think for the next 5 years, I don't think we will have a
More.
2% error solution.
Yeah. I mean, EDA always jokes about the customer's requests for automagical things. So, anyway, so let's thank the speaker.
Thank you.